Hello everyone. In this video, I'm going to talk about the orthogonality assumption. If you remember what we mentioned in class is that a violation of the orthogonality assumption implies that at least one of the regressors is endogenous. And then I said there are three reasons for endogeneity. The first one is omitted variables, then measurement error, and simultaneity. And what I said in class is that in the case of omitted variables, suppose that the true model is one for which, and we said, let's suppose that y refers to wages, and you're trying to find the association between wages and one explanatory variable x that we are going to refer as education. And q is another important regressor that we are going to say refers to cognitive abilities. The problem is that in many samples, you don't observe cognitive abilities in many observational data. And for that reason, the model that you are going to estimate is not the true model, but instead it will be this one, which is a model with an omitted variable, which in this case, we are excluding the cognitive abilities of this variable q. Now, the problem with this second specification in which we exclude the variable q is that q is actually relevant to explain y, and also q has an association with x, which in this example makes sense, right? So what we are saying is that individuals with high cognitive abilities are usually those who end up with a higher college degree, or let's say a master's or PhD degree, or at least that we know that they will continue being enrolled in school, right? It's less likely that kids with high cognitive abilities drop out. So you see the issue here is that these two variables or these two regressors are correlated. And at this point, we are wondering if we estimate the second specification in which we omit cognitive abilities or this important regressor Q, we would like to know whether the estimate of beta is consistent or not. So to evaluate this, we're going to compute the probability limit of beta hat, which is the estimate for the parameter beta. And what we know is that this probability limit is the ratio of the covariance x and y and variance of x. Interestingly, we know the value of y. Actually, what we know is that according to the true model, y is in fact alpha plus beta x plus gamma q plus the error term. Note, by the way, that in this model, in the true model, it has to be the case that the covariance, let's say, between x and epsilon is 0, right? Because that's the true value of the model. For the true, sorry, not the true value, the true model. For this model, we don't have a violation of the orthogonality assumption. The violation comes in the second specification where we excluded the regressor Q. Now, going back to the probability limit, of course, we have to divide by the variance of x. So what I'm going to do for simplicity is to first work only with the numerator, the covariance x and y. And then I will take the ratio between this covariance and the variance of x. Now for the numerator, we will form pairs between this x and all these other elements, right? which means that the first pair that we are going to form is X with alpha. And I'm going to write down all the steps here. If you want to skip some of those steps, it's fine as long as you understand what you're doing. But if you see here, what we have is covariance X alpha plus covariance X beta X plus covariance X gamma Q. And the last pair that we form is covariance X epsilon. We can continue simplifying, right? Because the first one is 0. And that's something that you already know pretty well at this point. We went over this during the review session. This is 0 because the covariance between a random variable and a real number or a constant is 0. There is no association. That makes sense. The other one that is 0 is this one, right? We mentioned that here. That's because for the true model, there's no violation of the orthogonality assumption. So we simplify this even more. What we will see is that the covariance X and Y is beta times covariance X and X plus gamma times covariance X and Q. What we also know is that the covariance of X and X is the variance of X. And this one, unfortunately, is different from 0. Why? Well, that's precisely what I mentioned here. That's the reason why this is an issue, because these two important regressors are correlated, which means that now we can re-express the numerator or this covariance X and Y as beta times variance of X plus gamma times covariance X and Q. And if we go back to the probability limit of beta hat, well, remember, this was a ratio, covariance XY and variance X. The numerator, that covariance XY, is precisely what we just found. And clearly, the denominator is just the variance of X. In other words, if you take, or let's say, if you divide each of the elements of the numerator by the denominator, and I'm going to write down all the steps. You can simplify it this way. First, right? I'm still missing one step. And finally, clearly what we have in the first element, and I'm gonna write this down again to have it beautifully in the same expression, is that variance of X divided by variance of X is 1, which means that the first element is beta. If this was the conclusion, clearly what we will say is that beta hat is a consistent estimate of the true value of the parameter. But in this particular case with omitted variables, it's not, because the covariance X and Q is different from 0. In other words, you still have this other element. And then in class, we talk about the potential direction of the bias, right? Which we said it depends on the sign of the association between the omitted variable and the dependent variable, and also the sign of the association between the covariance X and Q, which is the regressor in this example education and cognitive abilities, which in this case is the omitted variable. So we talk about those cases. Since this is the purpose of this video is to show you only these mathematical derivations, because we talk about intuition in class. I'm not gonna explain again the direction of the bias, but at least with this, with these steps, what we show is that the OLS estimator is not consistent when you have the omitted variables problem, right? So I could just write this down super quick to have the conclusion here. Say so the estimator is not consistent with omitted variables. Omitted variables in the sense that we're explaining here with these two main assumptions, right? Well, the first one is the assumption of orthogonality, but the other assumption is that this gamma is actually different from zero, because it means that there is a significant association between Q and Y, or that the omitted variable is actually relevant. And the second condition here for the omitted variables is that these two regressors are correlated, right? So if we define omitted variables in that way, then this statement is true, right? Which is what we just proved. Okay, now that's the one that I actually explained in class, but let's talk about the other case super quick. The measurement error situation. And for this one, we will consider two cases. Let me first give you some notation. What we will say is that the true model is Y star, where Y star refers to the actual value of the dependent variable, or values, right? Because these are vectors, but what we will say is that there's no mistake in the way we measure the dependent variable. And suppose that we are interested in this relationship between Y star and X star, where X star also refers to the measurement of this regressor without mistakes, right? With no error. But if we end up measuring it with error, then what we will have is that potentially, I'm going to say here with error, potentially we will have that there is an observation Y, which is the one without error plus the error term, right? So there's some noise that we observe in the data because someone made a mistake during the process of capturing the data, or because the respondent made a mistake, or for whatever reason, right? There is a mistake in the measurement of Y, and we will assume that this error term is distributed normal with mean 0 and variance sigma square V. We also have another expression for the error term in the case of, well, for the independent variable in this case, or the regressor X measured with error, which will be the one without error plus an error term, where that error term also distributes normal. now we are ready to look at the first case. The first case is a situation in which the dependent variable is measured with error. If that is the case, then what we will observe is that now my y is, and I'm talking about the model that we estimate, I'm gonna say that. Let me just check how I mentioned it before. We just said we estimate. Okay, so I'm gonna say my y is now alpha plus, and I'm gonna say beta x plus an error e, where this error e is the sum of the error that originally we had, right? Plus the error that comes from measuring y with mistake. But since y is located on the left-hand side of this equation, the error enters with negative sign on the right-hand side, right? So that's why instead of having u plus v, we will have u minus v. It's just, sorry, is the other way around, sorry. It enters with positive sign precisely because it was negative on the left-hand side. From here, what we will say is, well, we're interested in understanding if the beta that we have in the model that we estimate is consistent or not, the beta hat that we will get, right? So what we are saying is that we would like to know if the probability limit of beta hat is actually the true value of the parameter, in this case, beta. This probability limit is still measured in the same way we did before. Is the ratio of the covariance x and y and variance of x. And we are going to follow a similar logic as we did before, which is, why don't we just start with the numerator? In particular, in this case, since we know what is the measurement of the y that we are using, which is this model, right, with the respective errors, right? What we will say is that in this case, we'll have a covariance between x and the model that we estimate with the correct definition of the errors, right? In this case, it's alpha plus beta x plus, and now the correct definition of the error we said is u plus v divided by the variance of x. Now let me work with the numerator as I said before, which means that I will be working with this covariance x and y. Let's form pairs just as we did before. This is covariance x alpha plus covariance x beta x plus covariance x u, and finally plus covariance x and v. Now we can simplify some of this stuff because we know this is 0. Same as before, the covariance between a random variable and a constant is 0. We already know that this will be beta times variance of x. I'm going to skip that step now, because we explained it before. Now, what about covariance x and u? Well, covariance X and U is also 0. Why? Well, that comes from the true model, in which we knew there was independence here. I didn't mention it, but if you look at the definition of X with mistake, which is this one, well, we know that that error term associated with X is completely independent. That's what it's not explicitly written here, but we say IID, which refers to the distribution being an independent and identically distributed normal. So that's probably something that you saw in your statistics courses. That's why I didn't explain it with detail, but that independence allows us to explain that why this term is 0. And I was talking about the true model because in the true model is when we have X, right, and U together. So here, since X is, well, by the way, one of the things that I didn't mention, and sorry for that, is that in this case, in the case when Y is measured with error, what we are assuming is that X is not measured with error. So that is the reason. It has nothing to do with independence. It has to do with the fact that X is measured without error. Okay, so that's why. And for the last case, when we look at the covariance X and V, this is what I was talking about. Because of the independence. Why? Well, because you know that we are looking at the covariance between this regressor that is measured without mistakes, right? With no error. And V in this case refers to the error associated to the dependent variable or the measurement error, right? But this guy is IID, which means that it distributes identically and independently from other errors. And in particular, the distribution is normal, right? For each of the realizations of the error, the distribution is normal. Okay. So do you see everything is 0 except for variance beta x? Sorry, beta variance x, which is precisely what we wanted to see, because now when you compute the probability limit, which is the ratio covariance xy and variance of x, what you will have is in the numerator, we just have the green part, beta variance x. In the denominator, we have variance x. Boom, these two are 1, which means that we just show that how the OLS estimator is still consistent. And then you say, well, Professor, but it seems that there's no problem here, right? That's the conclusion, right? OLS estimator is consistent when Y star is measured with error. And I will say, well, yes, but there is a problem. And the problem is that we will be measuring with the variance of beta with an error. And that's precisely one of the things that I show on the slides. So I'm not going to go over everything, but if you go back to the slides, in the situation where I explain the case of omitted variables, which is this one. Omitted variables when y is measured with error. You see that it's less precise, and that's because the variance that I was talking about of your, in this case, now you are adding two variances, right? You're adding the variance of u and the variance of v, which are the errors of your regression. So now is the sum of these two. So that's the reason why it is measured with less precision, but in terms of consistency, we are good. So this is not really too much of a trouble, but we have another situation, which is when x is measured with, I'm gonna say, use the same notation with the stars, right? With x is measured with error. And as we did before, let's avoid any complications. Assume that y is measured without error, which means that y star is equal to y. Now this is the interesting case, because what we will have in this situation is that the model that we will estimate, or I would say we wish we estimate this model. And you can do the same for the other case, right? That was the original model, the true model. But unfortunately, I mean, the left-hand side is the same, no? I'm gonna say y only because we say that they're the same. But the right-hand side now includes my beta x, because remember, probably I should have written it here. My x is by definition x star plus w, right? If it is x star plus w, then it has to be the case that x star is x minus w, right? I just solve for x star. And I'm going to replace the value of this x star by the definition of x star, which is beta x for the first term minus beta w plus my error term. Again, if that wasn't clear, what I did here is that I plug the value of x star, which is the difference between x and w. And of course, since x star was multiplying by beta, each of these two random variables will also be multiplied by beta. So now we again are wondering if this estimate is consistent or not. So we will use once again the ratio covariance variance. In the case of the covariance, what we know is that y is in particular the model that we will estimate with the respective true values of the error, right? Well, I wouldn't say the true values. I would say the correct definition of the error, which now will be the combination of u, which is the regular error term, and beta times w, right? So let's write that down. In this case, what we will have is the alpha plus my beta x minus beta w plus u. And then you divide by the variance of x. This is the interesting part, because now what we are going to say is, okay, if we just work with the covariance, which is the numerator, we will be forming pairs. The first pair is x alpha. Second pair is x beta x, which at this point, you know clearly that that refers to beta times the variance of x. No? So that's simple. The third pair is beta times covariance x. Well, I don't know why I was doing this already in this, simplifying it. Let me write down all the steps. Covariance x beta w, right? And the last one is covariance x u. Some of these things will simplify. In particular, you already know this is 0. You also know this is beta times variance of x. You also know that this is beta covariance xw, which is what I was trying to simplify before, right? And for the last one, I'm not gonna say anything, but you cannot just assume in this case that it is 0, because now x is measured with error, right? So now we cannot assume assume that there is a 0 covariance. Some of the things will be simplified, and you will see. But in particular, we need to work with the definition of x, because we said x is by definition the true, well, not the true, but the x star, which is the measurement of the regressor without error, and its respective error, measurement error, which is w. In other words, you can simplify this as beta variance of x, and now minus beta. What's inside this covariance? Well, x and then w. But x, we said, is by definition x star plus w. And then my w, right? And you're going to do the same for the other covariance. In the other covariance, we have x, but x is measured with error. So x is my x star plus w, and then u. And once again, you're going to form pairs. The first element is still the same, but now here things become a little bit more interesting, because now we have beta covariance x star w minus beta covariance x star, no, x no, w and w. And finally, you have covariance x star u and covariance wu. Okay, so let's simplify some of this stuff. This one is 0. That was easy to see, because you know that the distribution of the error term That's the error term of the x, right? When it's measured with error. So it has to be the case that the covariance is 0. They're independent. This other one is, as we did before, beta, with respect to negative sign, no? Beta variance of W in this case. And this other term, the covariance x star u, is also 0. Now here is when we use the independence part, right? It is independent from the true model. Actually, we have it here, right? This is the true model. This is what we estimate. So from the true model, we know that there is no violation of the orthogonality assumption. So it has to be the case that the variance x star u is 0. And finally, the other term that we have is also 0. This is W and U. And that also makes sense because U is this error term. Oops. And W is the error term of X, which is this one. And that's the one that has that is independent from others. So that's why the covariance is 0. So now we have everything that we need. Let's go back to the probability limit. And I'm going to say, we said covariance x and y and variance of x. Numerator now is what we simplify from the last expression, which is beta, variance of x, minus beta, variance of w, divided by variance of x. Obviously, if you simplify this, we get that beta hat is the true value of the parameter minus beta variance of w, variance of x. And then some people from here, this is usually what I recommend you to do, is that they factor out beta, and this leads to 1 minus this ratio of variances. But the thing is that we know that the denominator is the sum of two elements because x is measured with error. So it has to be the case that you have the variance of the sum of two random variables that are independent, but two random variables, which means that we can simplify this probability limit as beta times 1 minus, here in the numerator, we still have variance of w, but in the denominator, you have the sum of the two variances, variance of x star and variance of w. And clearly, that element that is subtracting is less than 1, which means that this part here is also less than 1. And this is what we call, the intuitive part, which is what I explained in class, is that we said that the OLS estimator has attenuation bias due to the classical measurement error, no? Which basically means that you estimate towards 0. Okay. Next, and this is the last case, simultaneity. Oops. For simultaneity, we have interesting stuff. Everything like restarted. Let me fix this. There we go. For simultaneity, we have that the true model is one for which we evaluate the relationship between x and y. But it turns out that you could also explain x using y, right? I'm gonna include another regressor z, and the epsilons with their respective subscripts refer to error terms. I'm not sure if I was using like a similar notation in the notes. If not, sorry for that. We can always change it in terms of the Greek letters for the for all these parameters. So that shouldn't make any difference, right? What matters is that we have these two different equations, suggesting that, as I said before, you could explain x using y or y using x. That's a simultaneity issue. And we would like to know if the probability limit of beta hat is the true value of the parameter. And for that, we're going to use the ratio covariance variance, just as we did before. But in particular, if you look at the numerator, this covariance is the covariance between x and the true model for y. The denominator is still the variance of x. Now let's work with the numerator only. In this case, what we have is that we will form pairs as we did before. At this point, you should be experts doing this, right? We've done it many times. And you already know what things simplify, which is also cool. For example, you know that this is 0. You also know that this one is beta times the variance of x. But we don't know anything about these other terms, right? At least the only thing that we know is that it's different from 0. And the reason why it's different from 0 is because you can no longer use the orthogonality assumption for these two, because turns out that y is also explained, sorry, x is also explained by y. So this y here, I'm going to put it in red. This y here contains epsilon 1. So no, you can no longer say that the covariance between x and epsilon 1 is 0, which means that if we go back to the probability limit, we have that this is beta variance of x plus covariance x epsilon 1 divided by the variance of x. So this was easier, right? Because now, conclusion, here we have that the probability limit of beta is the true value of the parameter plus something else, which in this case is this ratio of covariance x epsilon 1 and the variance of x. So we are going to say that the OLS estimator is not consistent with simultaneity. And those are all the cases. Now you have each of them. I will say if you have any extra, like any additional questions that you would like to understand, details of anything better, you always have the opportunity to ask using the office hours, right? I will have office hours on Monday, the day before the exam, but also you can ask the TAs. So don't forget that you also have that option. Well, I hope this video was useful, and see you next time. Peace out.